Welcome to my talk. The talk title is Pouring Salt into the Crypto Wound, How to Not Be as Stupid as Ransomware Offers. My name is Sarah W., but I more oftenly go as Polar Toffee on Twitter or Toffee. I'm a malware researcher at MSoft, and I've been following ransomware for about 7 years now. This is also my first talk, so be kind. So quickly I'll go through the agenda. I don't know how many people in the audience are familiar with basic cryptography terms. Raise of hands, if anyone's familiar. Okay, so about good number. For those of you who are, this first section probably won't be nothing will be new to you. But if not, for the people who aren't familiar, it will kind of catch you up with the rest of the talk, as it's kind of important. The majority of the talk will be focusing on mistakes made in ransomware. All the ransomware families that I'm talking about today have long since stopped operating. However, their mistakes are universal, and it even applies further than just ransomware to general cryptography. Finally, I'm going to provide some basic pointers about when using cryptography in your own projects, what mistakes not to make so you don't look as stupid as some of the ransomware authors in this talk. So moving on to the commonly used terms and their meanings. In cryptography, whenever we talk about a message, we are referring to the data that we want to encrypt. Usually it's either some text or a file. Plain text is the unencrypted version of the message, and ciphertext is the encrypted version of the message. The encryption algorithm turns the plain text into ciphertext, and vice versa. And this is known as the cipher. Ciphers take plain text and ciphertext and use the keys to turn it into its relative counterparts. Broadly speaking, there are two major types of ciphers. Symmetric or secret key encryption uses a single key to both encrypt and decrypt a message. Common examples are AES and RC4. The other major cipher is asymmetric or public key encryption, and the difference is it uses two different keys. A public key that is used to encrypt messages, and a private key is used to decrypt messages. So moving on, the first, so symmetric ciphers are divided up into two major groups. The first group is called stream ciphers. The basic idea of a stream cipher is that a key will then seed a random number generator, and this random number generator will then spit out a long stream of values, which is deterministic, which is based on the key. This stream of random values is known as the key stream. Each bit of the key stream is then combined with its corresponding value in the plain text to turn it into the ciphertext, and vice versa in terms of decryption. The operation that is commonly used to combine these bits is known as XOR. The most commonly used stream ciphers are RC4 and SELSA. So stream ciphers have one golden rule, and this will become important later on in the talk. Never reuse the same key twice. The reason for this is relatively simple. If you have a single plain text and its corresponding ciphertext, it is possible to get the whole key stream, return to the key stream by just XORing the ciphertext and the plain text together. And then if you reuse the key, then you can then use this key stream to decrypt all other keys that have been used for the same key stream. The other large group of symmetric ciphers are block ciphers. As the name implies, these ciphers work on blocks of data. Often the block sizes are 8 or 16 bytes. Block ciphers use a key to transform the plaintext blocks through various rounds of substitution and permutation. There are a couple of different block ciphers out there. Triple Des, Blowfish, T, and AES are the most common. However, block ciphers have one problem. If you encrypt each block using the same key, then identical content in the plaintext will result in the same encrypted, be identical in the ciphertext. This then reveals structural information about the encrypted message. The picture you can see on the slides here is known as the ECB penguin, and it demonstrates this problem quite well. The left image was then encrypted just using a block cipher only, and you can see that the image it produces on the right, whilst missing some of the important details and colours, it still has the outline of the penguin. So this is where block modes come into play. Block modes are additional steps that are performed between two blocks, so they end up appearing random, and you don't get structural information like this appearing. But what do we do with the first block? The solution is to use a random block at the beginning, known as the initialization vector, or IV. And that is then used to perform the transformation on the first block of the plaintext. There are a few common block modes, ECB, which is no block mode at all, CBC, which is each block of the plaintext is XORed with the previous ciphertext block. CFB, OFB, and CTR turn block ciphers into stream ciphers, and this comes with all the disadvantages and advantages of stream ciphers. There are a few specialized block modes, such as XTS, which is specifically used for disk encryption. So moving on to random number generators. There are two types, pseudo-random number generators, PRNGs, and true random number generators, TRNGs. TRNGs are based on physical phenomena which is believed to be truly random. One example that people may have heard of is that Cloudflare uses a bunch of lava lamps on a wall to generate random data, as lava lamps, the physical properties of the movement of the lava lamps, they take photos of them, and that photo then is transformed into random data and used to seed the pseudo-random generators that are used for cryptography, and that's believed to be truly random. The pseudo-number random generators are use an algorithm to produce long sequences of values, and they appear to be random, but in actual fact usually aren't. So a pseudo-random number generator is fed an initial value known as a seed value, and then it will spit out a specific sequence of numbers. If you use the same seed value multiple times, you always get the same sequence of values using the same pseudo-random number generator. So why don't we use true number TRNGs all the time? The issue with that is TRNGs are time limited. So there's only so much random data that you can generate within a specific period of time. To get around this, we then use a true random number generator to seed the pseudo-random number generator, and this can be used to create as much random data as needed. Pseudo-random number generators can be separated out into cryptographically secure and cryptographically insecure. And this just means whether they can be used safely for cryptography or not. Most default random number generators in programming languages are considered insecure and should never ever be used in proper cryptography situations. One thing to note is that secure pseudo-random number generators can be made insecure if not seeded properly. So, moving on to the first category of mistakes in ransomware, hoaxes and diversions. In reality, these are very low-effort ransomware. So the first two examples, the top one refers to Nemucod and the second one refers to CryptConsole. In the first Nemucod version, they use the batch script, so you can see how much effort they put into their ransomware. The batch script basically just enumerates through all files that have a specific extension that they listed on your C and D drives, and then just renames them with the .encrypted extension. In the second example, CryptConsole does a little bit more, but again, it's not much difference. So in this case, they just encrypt the file name using AES with a hard-coded key in IV, which is insecure, of course. and then they rename the file name to the new encrypted name. In both cases, the file content is never touched. So, simply renaming a file is not at all cryptographically secure, as one can imagine. The file content is not touched, it's never encrypted, so it's possible to just rename the files back to fix the issue. So, lazy effort ransomware was often paired with extremely low ransom demands, in the hopes that people would rather pay the $35 that Nemicod, for example, asked for, rather than trying to rename the files manually. Okay, moving on to custom algorithms. So it didn't take people long to figure out that Nemicod just renamed files and didn't actually encrypt them. And the ransom authors eventually caught on and figured out that they would have to do something different to get people to pay. So this was the second version that they tried. In this case, they just check if the file size is bigger than 2048, and if so, limit the bytes to encrypt to 2048. Then they check if the encrypted, if they have already encrypted 2048 bytes, and if so, then just move on to displaying the ransom note. If not, then they will read the next byte from the file and then XOR it with the corresponding byte of the key. And then they will seek back one byte in the file to overwrite the byte, and then just read, and then increment the encrypted bytes counter. The ransomware will then continue looping through this algorithm until it's either reached the end of the file or encrypted up to 2048 bytes. Merry Xmas was another ransomware that tried the whole custom encryption. In this case, as you can see, it's a bit more complicated, but the principle was still relatively similar. The algorithm is that each byte in the buffer that holds the plain text is being encrypted by adding the corresponding byte in the buffer with the key, multiplied by a couple variables such as where in the buffer the key is, the length of the overall buffer, and the length of the key. They then pick a new key index and move on to the next byte in the buffer. The way they coded the ransomware was a little bit flawed in that they always end up skipping the next character in the key. This means that the first byte is always encrypted using the first character in the key, but when they moved on to the second byte that they tried to encrypt, they then used the third character in the key. The key never changes, so it's possible to attack this algorithm one character at a time. As I mentioned before, half the key is never used, so the key index is never even. This means that each character in the key only has 128 possibilities, and so, for example, for a 12-character key, there's only 6 times 256 different combinations, which is laughably easy to brute force within seconds. So, to sum things up, custom algorithms and custom implementations of existing algorithms rarely turn out secure. In Nemicod's case, they just XOR the file data with a fixed-length key. So it's very easy to calculate the key by XORing a known encrypted file with its original version. And this then can be used to decrypt all other files. The Merry Xmas ransomware performs some basic reversible arithmetic operation to encrypt each byte using a corresponding byte in the key. So a single known plaintext and ciphertext pair can then be used to attack each character in the key separately, and you can recover the key in seconds, like I mentioned before. Moving on to static or semi-static keys. So meet DMA Locker. DMA Locker is a ransomware family that's going to come up a few different times because they had a few different goes at cryptography before they got it mostly right. So DMA Locker had a relatively good first iteration. They used AES to encrypt files, and they used a commonly reviewed implementation of it. That was fine. However, where did they get the key from? If you look at the function, they actually just open the exe that corresponds to the process and then seek to the end of the file, reading the last 32 bytes. If we look at the second screenshot, you can see what looks like a key in the last 32 bytes, and that's exactly where the key is located. Sometimes ransomware authors think it's a good idea to generate the key based on system configuration, and I can see why they think that. CryptoHost was one such example of this. They take the processor ID, the volume ID of the C drive, and the motherboard UUID, and then generate a SHA-1 hash with it. They then concatenate the SHA-1 hash and the current username and use this as the key. So what can we learn from these examples? Well, strong ciphers are useless if the key isn't kept secret. In DMA Locker's case, they use a static key that the author switches out for each campaign. So as long as at least one user per campaign is able to recover the exe file, it's trivial to just take the key from the end of the file and then use that to decrypt all victims that were hit by the same campaign. In CryptoHost's case, it's possible to derive the key based on the system's configuration, so it's very easy to re-implement their same algorithm, and then you can run the decryptor on the same system that was hit by the ransomware in order to generate the key. A lot of people think that they can get away with shortcuts such as these by obfuscating the code. However, in reality, even the most complicated obfuscation is not enough to stop the most dedicated person. So, key generation mistakes. Key generation mistakes are one of the most common mistakes that we've seen in ransomware. So this is DMA Locker version 2. They tried again, and they decided to use random keys. So in this case, they decided to use the rand function to try and generate the random data used for the key. So they use rand to generate a random number and then map it to a value between 1 and 100. If the random index is less than 25, then they'll generate a second random number, again using rand, and then map it to a corresponding character between lowercase a and lowercase y. If the random index is less or equal to 50, but bigger than or equal to 25, they do the same thing, except they map it to the characters between 0 to 9. In all other cases, they'll generate a random number and then map it to a corresponding character between uppercase A and uppercase Y. This is then repeated 32 times to generate the 32-bit AES 256 key that they then use to encrypt each file. The issue with this is, as I mentioned previously before, the rand function is an insecure pseudo-random number generator. And it uses the 4-byte integer time of execution as its seed. This means that there is only slightly more than 4 billion different combinations that rand can produce, and this means that the number of keys is only limited to slightly more than 4 billion that the algorithm can ever produce. So the bottom line is that key generation is not as easy as it looks. For example, random, you would think, would be random, but it isn't always. The authors thought that they migrated to a random key, but as I mentioned before, they actually didn't. Instead of ending up with 2 to the power of 256 different possible keys, they only end up with 2 to the power of 32 different possible keys. And this is brute forceable within half an hour on most modern systems. So relatively easy for users to get their files back. Key reuse. It's dangerous to reuse the same key for everything. GetCrypt was one example of a ransom family which decided to do this. In GetCrypt, they generate a single key which is used to encrypt all files using this specific algorithm. They read 8 bytes from a file and then encrypt these 8 bytes using salsa 20. And then they move the file pointer back 8 bytes and then write these encrypted bytes into the previously generated read bytes. And they repeat this until they either reach the end of the file or encrypted 128 kilobytes, whichever comes first. The problem here is salsa 20 is a stream cipher. And remember what I said about stream ciphers. Never reuse the same key twice. This makes it so all you need is a single plain text and encrypted ciphertext, which are at least 128 kilobytes in size, and then you can XOR these files together, XOR the first 128 kilobytes of these files together to recover the key stream. And then you can apply this key stream to every single file that was encrypted by the ransomware to recover all your other files. DMA Locker, again, had a third try at ransomware. They fixed the key generation flaw in the third iteration of the ransomware, but however, they still made a mistake. They didn't get it completely right. Each per file key is encrypted using the same public static key that is shared between each campaign. And this is then installed in the encrypted file. So this means that for a victim to be able to decrypt their files, they do have to pay the ransomware offer to get their private key. However, this private key will not match just the one victim system. They will match every single victim that was hit by the same campaign. So instead of every single victim needing to pay, only one victim needed to pay. Guess they didn't think that was going to happen. So the bottom line here is always be careful about key reuse when dealing with asymmetric encryption or stream ciphers. Not reading the fucking manual. So Crypto Defense did everything by the book. They generated keys securely, they didn't reuse the same public key, and they generated a new key pair for each system, as it can be seen in the code here. However, they still made a small mistake, and that small mistake turned into quite a big mistake for them. They didn't read the documentation properly. So what does the documentation say? It says this. It looks like it was big enough. You might be able to, it's a lot of text unfortunately, maybe you'll be able to spot the mistake they made. Or if you're familiar with get, verify, crypt context. So Crypto Defense copied the code for the Microsoft example that they have on their website. And in this case, the example didn't have the crypt verify context flag set. So reading from the documentation, in terms of what this says about crypt verify context, it means that when this flag is set, the temporary public and private key pairs can be created, but they are not persisted. So if the flag is not set, they are actually persisted and then saved on the system. Double negatives to the win. So this is exactly what happened in the case of Crypto Defense. All Crypto Defense victims had the RSA key pair still left on the system. And as a result, it was trivial to find the known location of the keys and then use this to restore all the files. The Crypto Defense authors would have never known that they'd made this mistake if a certain AV vendor didn't release a public blog post detailing the flaw a few days after a decryptor was made. Never detail the flaws of an active ransomware campaign publicly because they will take advantage of you telling them where their mistake is. One fun fact is that the Crypto Defense authors were so embarrassed by their mistake and so upset by the bad publicity that the free decryptor caused is that they decided to rebrand their ransomware as CryptoWall. CryptoWall was one of the most prevalent ransomwares in 2014 and is still one of the most prevalent ransomwares that we've had to date. I believe they made over 100 million US dollars, but that figure may have been way more. That was just an estimate. Attacks on the command and control servers. Last but not least, let's have a look at the last commonly mistake of ransomware. So some ransomware do everything right in terms of cryptography, but they manage to do everything wrong in terms of the server that stores the keys. One example of this was MegaLocker. MegaLocker operators didn't know how to manage MySQL without help, so they decided that they were going to use PHP MySQL admin, which is fine. They thought that just using a random directory with no authentication would be enough security. Of course, they should have thought again. With a few clicks, it was very easy to find and dump all of their victims and keys. GandCrab is another example of ransomware that was owned in the same way. One thing to note is also old versions of PHP, MySQL, and other website managed platforms tend to have vulnerabilities, and that's another way to get owned. And previous other ransomware have got owned that way. But sometimes it's not always as easy or simple as this. Spora was one example of a ransomware which was quite unique. They had a portal where you could live chat to their operators, which was interesting, but it also worked out quite well for them. They also gave discounts if you wrote a good review on Bleeping Computers. I think it was like 10% off or something. Interesting. So the Spora did basically everything right. They generate a new RSA key pair for each system. They create a block of information that contains the key pair as well as some metadata about the system. They then encrypt this information block using a randomly generated AES key and use that key in EBC mode to encrypt the information block. The AES key is then encrypted using a public hard-coded key, and both the encrypted AES key and the encrypted information block are stored in what they know as a .key file. So the victim, when they wanted to try and decrypt their ransomware, would have to upload the .key file to the author's portal to try and get their files back. The portal would then decrypt the AES key in the key file using the author's private key. It would then use the AES key to decrypt the information block and then extract some information from there and display some of this on the portal. As you can see, the block date is the infection date and the username is from the system. That's some of the information that was stored in the information block. Upon payment of the ransomware, a decryptor would be created using the system's private key pair. So you might be wondering, what mistake did they make here? Well, just because something is encrypted doesn't mean it can't be messed with. Since the authors use ECB, it's possible for us to move the blocks in the ciphertext freely without messing up the ciphertext. So what happens when we move the blocks that contain the private key into areas that were stored the username and infection date in the portal displays? Well, it then displays part of the private key instead. So within about 10 to 15 different manipulated key files, it was possible to get the whole private key back. And then this could be used to decrypt the user's files. So what is the lesson to be learned here? It's not necessarily the encryption that can be tacked. Just as often it can be your infrastructure. So your crypto is only as secure as your operational security is. Also beware that encryption doesn't guarantee that what you're trying to decrypt hasn't been messed with or will be messed with. So how to not be like ransomware authors? This is where I'll give you some tips on what not to do. First of all, never roll your own cryptography. As Bruce Schneier puts it nicely, anyone from the most clueless amateur to the best cryptographer can create an algorithm that he himself can't break. Coming up with your own cipher and also implementing a known cipher yourself securely well is quite difficult. It's better to use established and reviewed libraries. I would suggest using libraries that are easy to use and that make a lot of decisions for you. Also, don't copy and paste code that you do not understand. For example, the person whose cryptography code that you copied from Stack Overflow is probably about as clueless as you are on this. So another thing to note is don't copy code from the documentation unless it specifically states that it's cryptographically secure and should be used as boilerplate. If an example API that you're trying to use is too complicated, use a different library. Be aware of the limitations of algorithms that you use. If you're using a stream cipher, don't reuse the same keys or you'll end up with big issues. Using a block cipher, make sure you're using appropriate block mode. Generating your own keys, make sure you use a good source of randomness. And finally, try and break systems that you come up with and encourage others to as well. Look at similar systems to yours, see what they use, and see what security issues they encountered, and try and learn from that. It's cheaper to learn from other people's mistakes than to have to deal with the issues when you've made your own. Few shout outs to Fabian Wosar. He's my boss, but he also helped massively with the content of this. Demon Slay, Malware Hunter Team, and Bleeping Computer, all great sources for ransomware news, and in general, amazing people for fresh intel. Any questions?
Can I ask one? What happened with the case of the city of Buffalo then? The city of Buffalo has been hit by ransomware and still can't seem to crack the code.
So there's a lot of ransomware which do everything right. A lot of in general, if you use a well-known encryption algorithm and that's and you generate your keys properly, there's nothing we can do. Unfortunately, you end up having to pay the ransom. Plenty of city councils, police. I think even the FBI at one point recommended that you do pay the ransomware, and then they changed their kind of statement on that. So unfortunately, if your backups are not in good state, either they're outdated, don't work, or they don't even exist, then if you need that data, you're going to have to end up paying the ransomware and hoping that the criminals will give you a working decryptor and a proper key. Because there's plenty of times where they've either made off with the money or they provided a decryptor which is faulty, doesn't work. So sometimes it happens that some of the white hats that work on this end up having to make a decryptor that fixes the ransomware author's problems. Yeah.
How often do you come across cases where they do everything right in terms of the crypto, but they do the key generation locally and leave the private key material or something like that in the heap?
That's a good question. Not very often, actually. Most of them, there's a lot of if you have logging systems in the for example, some ransomware send out their keys to the server. Or the keys are generated on the server and then sent to the ransomware. So, for example, you had something like Wireshark running and you captured the packets. As long as it wasn't encrypted, you could then grab the key. But in most cases, most people don't have that kind of capability running or just don't think about it. A lot of ransomware, there have been cases where they had left the keys on the system, but they tend to usually think to delete them. That's one of the few things. More often they make a mistake in either reusing keys or how they generate the keys. I guess there's no more questions. Thank you very much for coming. I hope you enjoyed the talk.